In this module, we are looking at a fundamental simulation concept called the initial transient period. And for this example in particular, we're looking at the bias that this initial transient period can cause when we use our simulation model to estimate performance metrics for our system. The system we're going to look at is called a penny fab, and it was originally introduced in the factory physics book by Hopp and Spearman. And this is an example of what's called the CONWHIP production control strategy, and CONWHIP stands for constant whip. So you can see I have my single server and I have a queue of raw material waiting to be processed. And so this is essentially, you have penny blanks that are waiting to be stamped into fully formed pennies. And instead of having external arrivals like we do in our traditional queuing system, instead the completion of one penny causes the introduction of a new blank into the queue. And so we maintain a constant value of whip. In this case, we have a CONWHIP number of 5, right? So at all times, we're going to have 5 entities in our system. And our objective, before I get to the objective, let me also say that we're going to assume that we have deterministic processing times of 1 minute. Our objective is going to be to estimate theta, which is the expected value of time in system at steady state. So once the system is run and achieves steady state, we'd like to know how long does the average penny spend in the system. That's what we're going to call theta, and we'd like to use simulation to estimate this value of theta. Since we have such a simple system, we're just going to simulate the first 10 pennies to our system, and we're going to do that manually. And so what I'm going to do is I'm just going to track this value of interest. And so by penny, so this is penny I, and we're going to do the first 10. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'd like to know how long does each one of these pennies spend in the system. So this is going to be time in system I. We'll have 1, 2, 3, 4, 5, 6, 7. And these are in minutes. Okay? And so we can do this. As I said, the system is very simple. This is one reason we have deterministic processing time, so that we can make this process easy. So the system starts here with 1 penny ready to be stamped and 4 pennies in the queue for our constant whip value of 5. And so when we start simulated time 0, the first penny is going to finish at time 1, the processing time. And so its time in system is exactly 1. Once penny 1 finishes, it signals the 6th penny to get in line behind this last one and to start processing of the 2nd penny. So the 2nd penny will then finish at time 2, and so its time in system is exactly 2. When it finishes, we start processing for the 3rd penny. So the 3rd penny waited for the 1st penny and waited for the 2nd penny and then was processed. So it spends 3 units of time in the system. The 4th penny spends 4 units of time. The 5th penny spends 5 units of time, because that 5th penny, again, waited for pennies 1, 2, 3, and 4 for 4 minutes and then was processed for 1 minute. Now, the 6th penny didn't get created at time 0, right? The 6th penny gets created when the 1st penny finishes. So the 6th penny also takes 5 minutes. The 7th penny takes 5 minutes. The 8th penny 5 minutes. The 9th penny 5 minutes. 10th penny 5 minutes. And as you can hopefully see, the value that we're trying to estimate, we can just look at and tell. This turns out to be exactly 5. But we're going to pretend that we don't know this, right? So we can see this, but we're going to just pretend that we don't know that. And so instead of being able to just look at this and say the answer is 5, we want to use our typical simulation method so that we can estimate this value of theta. So I have 10 observations of time in system, and what I'd like to do is estimate this value of theta. So typically what we would do is we would say, well, I'm going to have theta hat, and my theta hat is based on 10 observations. And I'm simply going to take the numerical average. So I'm going to have 1/10 of 1 plus 2 plus 3 plus 4 plus 5, 5, 5, 5. Let's see, so that's 1st, 2nd, 3rd, 4th, 5th, 6th, 7th, 8th, 9th, and then finally our 10th penny. Right? And so if you do this, you're going to get 1/10 times 5, 10, 15, 20, 25, 30, 35, 40. 40. So our estimate of theta hat, or our estimate of theta, is 4. Well, again, we know theta has an exact value of 5, right? And so we might say, well, let's add more pennies, right? Let's just do more. So for example, let's suppose we calculated theta hat for the first 100 pennies. Well, what we're going to end up with is 1 over 100, 1 plus 2 plus 3 plus 4 plus 96 times 5. So we know once that fifth penny arrives, all subsequent pennies are going to spend 5 minutes, 5 time units in the system. And so this ends up being 4.9. So we're closer to 5, but we're still not at 5, right? So, okay, well, let's try more. If we did theta hat of 1,000, we end up being 4.99. Okay, and so again, we're getting closer to 5, but we're not at 5, right? And one of the fundamental concepts here is based on our deterministic processing times. Using this method, we will never get to 5, right? So what I'm saying is that our estimate of theta hat for n will be strictly less than 5.0 for any finite value of n, right? So this fundamental relationship is true for any value of n. So I can't simulate my way out of this initial transient. And so this is what's called the initial, or the bias caused by initial transient, in that our estimate, the way we've done this, is going to be downward biased from the value of 5. So let me erase this so I can use the board here. So I'm going to erase this, all of this, which we know now, and introduce a second method to estimate theta. This time what I'm going to do, well, let me erase this right here. This time what we're going to do is we're going to define theta hat in L, where L is going to be defined as our warm-up period, is equal to 1 over n minus L times the summation I equals L plus 1 to n of TISI. Right, so instead of using all of the values, what I'm going to do is I'm going to chop off the first L values. Right? So for example, suppose I let, in our case, suppose I let L equal 5. Right? So I'm going to have theta of 10 5 is equal to 1 over 10 minus 5 summation I equals 6 to 10 of TISI. And so this is simply going to be 1/5 of 5, 5, 5, 5, 5. This is the 6th penny, 7th penny, 8th penny, 9th penny, 10th penny, as we see right here. So 6, 7, 8, 9, 10. And of course, now this equals exactly what we know the answer is, exactly 5. So what we've done, in essence, is we've eliminated this initial transient period from our computation of, or our estimate of the value of theta. Okay, so of course, hopefully anyway, the natural question now is, well, how do we choose theta? In this case, it's obvious because we have a nice, easy deterministic case that, we reach steady state right here at 5, right? So in the general case, when we have stochastic components, it's not going to be nearly that simple. So in choosing L, we're going to ask ourselves two questions. The first thing we're going to say is, well, suppose I pick an arbitrary L and it's too small. So like, for example, in this case, instead of 5, suppose I pick 2 as my value of L. Right? If I've done that, then I'm going to have values from pennies 3, 4, 5 up to 10, and the result will be that my estimate of theta will still have that downward bias. Right? So my estimate will still be biased if I pick the warm-up period to be too small. On the other hand, what happens if I pick the warm-up period to be too long? So instead of picking my value of 5, suppose I pick my value of 8. Right? And so if I pick the value of 8, then I'm going to have pennies 9 and 10 in our estimate. And in this particular case, we will get the exact value because everything is deterministic. However, what we're doing when we make L too big is we're essentially throwing away usable data. So when I pick a value of 8, I'm throwing away the 7, the 6th, and even the 5th penny that we have already reached steady state, right? So I'm eliminating that value. I'm eliminating that usable data. And where that becomes important is when we incorporate that into our standard confidence interval, right? And if you recall, we have something called the standard error, right? And our standard error from sampling is equal to the sample standard deviation divided by the square root of n, right? Divided by the square root of n. And so when we compare our normal, our regular standard error to our modified standard error when we use the warm-up period, we're going to have Sn over the square root of n versus S n minus L over the square root of n minus L. And because L is a positive number, the resulting standard error is going to be larger than our regular case. Now, when I say larger, I mean that in the probabilistic sense. If we do many of these, it will be larger. You might have one individual observation where it doesn't follow that, but probabilistically speaking, it will always be larger. Right? And so the net result is when we incorporate our standard error into our confidence interval, the confidence intervals here for this method will be wider. And so the result of that is that I might have to run my model longer. Right, so the payoff that I get when I have a longer warm-up period is that I ensure that I've removed the initial bias, but the cost is that I might have to run my simulation longer in order to get the confidence intervals narrow enough to where I can be confident in the results that I got. And so we see here that because we are interested in steady state performance, but we start the system in what's called the empty and idle state, right? We started the system somewhere. We have to get to steady state before we start tabulating the results. And this period here, prior to getting to steady state, is what we call the initial transient. And our calculation, our estimate of this expected value, because these values are always lower, then we'll end up with a downward bias in our estimate, regardless of how long that we run the simulation for. And so what we did was we said, well, let's just eliminate all of this data. Let's just get all the bad data and get rid of it. And then, of course, as we just discussed, the trick there is to figure out, well, what am I going to lift the value? How much data do I get rid of? So in the next video, we'll look at this model using Simio. And we'll build this model and we'll talk about, well, how do I implement this notion of getting rid of the initial bias, which involves using what's called a warm-up period.